All right, so before the break, we were talking about specific heat capacity and we were talking about latent heat. So quick review. When we are looking at the amount of energy that changes when there's a temperature change, we are dealing with kinetic thermal energy. So if we are looking at this graph for something like that, okay, any part of the graph where the line is going up, okay, so right here, okay, right here, and right here, we are changing the kinetic thermal energy of the material. If I want to calculate how much energy is used during those sections, what formula do I use? Okay, yes, but they both go that way. It's M thing. I use that right here. No. Okay. E equals MLF is how I calculate the amount of energy involved in changing state from solid to liquid or from liquid to solid. Okay. That's the latent heat of fusion. Okay. That's what happens when we're melting and freezing. Up here, I would use the other one that has to do with that, which is E equals MLV. Those have to do with potential thermal energy, right? Because remember, during a state change, evaporating, condensing, freezing, or melting, okay, there's no change in temperature. So there's no change in kinetic thermal energy. I would use E equals MC delta T for these sections here, okay, where the line is going up and there is a temperature change, because the formula involves temperature change and we are using kinetic thermal energy. Okay. What do I need to be aware of when I'm using E equals MC delta T on this graph? The type of material. Okay, now this is the heating curve of water. It's always water. So why am I concerned with what material it is if it's always water? Yeah, exactly. Water is one of those weird things, polar molecule. As a result, its specific heat capacity, C, is different when it is a solid, when it is a liquid, and when it is a gas. So you have to make sure you're using the right specific heat capacity for each section of the graph. That's a very common mistake. The most common mistake that people make is with the temperature change, however. Okay, if I am heating ice from minus 25 into steam at 125, okay, I'll often have people tell me that the temperature change for this part of the graph is 150 degrees. Is that true? No, that's the temperature change for the whole question, but the last time I checked, you don't usually have ice at 125 degrees. Maybe for a short period of time, but not, okay, it's not going to be there. The ice is only going to change from minus 25 to 0. So its temperature change for this section would be 25 degrees. For this section, it would be 100 degrees. And for this section up here, it would be 25 degrees. Okay, everyone all right with that? Now, with the MLF and MLV, okay, if we're dealing with any state change that involves melting or freezing, okay, so going from solid to liquid or from liquid to solid, the amount of energy needed or the amount of energy given off, if we're talking about freezing, can be calculated by going E equals MLF, okay, where M is the mass in grams, and LF is the latent heat of fusion of water. The latent heat of fusion of water is 333 joules per gram. Okay, that number will be on your exam. It will be on your final exam formula sheet. I know that because I printed them over the holiday. Okay, I made sure they're all on there. Okay, questions on that? So that means that to change 1 gram of ice into 1 gram of liquid water already at 0 degrees Celsius requires 333 joules of energy. Okay, now maybe over the holiday, maybe not, because it was wickedly cold the whole holiday. Okay, maybe you went outside and you put your hands in the snow, or you made a snowball or something like that. Okay, do your hands get really, really cold when you do that? Yeah. Because what's happening to the snow when you put it in your hands? Well, first it raises its temperature to 0. Then it starts to melt. Ice doesn't melt until it gets to 0. Okay? Once it gets to 0, then it starts to melt. For every gram, and 1 gram of water is 1 milliliter. Okay? So it's not very much. For every gram of that snow that melts into water in your hands lose 333 joules worth of energy. Okay? So it's a lot. That's why your hands get really cold really fast. Everybody follow? If we are talking about, sorry. It wouldn't be in newtons. Newtons is force. How many joules? Depends how much ice. Okay, for every gram, it's 333. So if I have 2 grams, it'll be 666. If I have 3 grams, 999. Yeah? Okay. Now, if I want to change state from liquid to gas, and this is the latent heat of vaporization. This is the latent heat we talked about back when we talked about climate and energy transfers and things like that. Okay, to evaporate 1 gram of water, that's 1 milliliter, requires 2,260 joules worth of energy. Okay, is that a lot? Yes. So does a moist air mass moving from an equatorial area to a more polar area bring with it a lot of stored energy? Yes, because there would be millions of liters of water in that warm air mass. Okay? And every liter of water, sorry, that's too many. No, it's not. That was right. That 2 was right. Every liter of water, okay, is going to have 2,260,000 joules worth of energy stored in it, and will release that energy when it condenses back into a liquid. Okay, so remember how we said latent heat was a really important way of transferring large amounts of energy via the jet stream from equatorial areas? Something you might want to be able to explain on your test on Thursday. Okay, this is why. Okay, this is the math of it. Water carries a lot of energy with it if it's a vapor. All right. To calculate the amount of energy required to evaporate water, or that water would give off when condensing from steam back into liquid, okay, we would use this formula here, E equals mLV. Okay, M is again the mass in grams, and this number is LV, 2,260 joules per gram. Everybody with me so far? Okay. Is it possible to get liquid water below 0 degrees Celsius? Yes. Okay. You guys ever put like a bottle of water in the freezer? Okay. And you go back like a day later and it's still a liquid? Okay. If you put it in there just right and there aren't too many bubbles in it and doesn't get agitated very much, it'll stay a liquid if it's really pure. Okay. Especially if it's like RO water. Okay. If it's been purified using reverse osmosis, it has basically no particulates of any kind. Okay. You can supercool it. And you can get it down minus 15, minus 20. Okay. If you have exceptionally pure water, you can cool it down to minus 45, 50. Okay. I remember this because my chemistry prof, was one of the few things I understood in the whole course, okay, in university, brought in this like really cool looking vat that was like steam was coming off it. There was ice all over the outside, had liquid nitrogen inside of it, okay, and it was keeping this vial of liquid water super cooled, and he set it on the counter, and then he pulled this, he unscrewed the top and looked like something out of a science fiction movie, pulls this, the top comes off and more vapor comes out, and it was really cool. Okay, anyway, he pulls this vial of liquid water and sets it very carefully on the table at the front, and he says, so we have liquid water here, and it's like minus 45 degrees. It's very, very cold. How is that possible? And everyone's like, well, it's not. Water freezes at 0. That's ridiculous. You got something in it. Okay? He said, nope, this is just extremely pure. And the lesson was about crystallization and seed crystals or something like that. Okay? He said, all I need is 1 seed crystal in this water, and it'll freeze instantly. So he took a little bit of salt and dropped like 1 grain of salt onto this thing, and the dish it was in exploded. Okay, because the water flash froze. It froze in under a second, turned into a block of ice. And of course, ice expands, so it shattered the container. Okay, it was a pretty cool demonstration, unless you were in the front row. I wasn't. Okay, but yeah, it was. So he flash froze this water. So you can super cool this stuff. Okay, but was a lot of energy released when that happened? Yes. Okay, because liquid water still, even though its temperature was below zero, still had all the potential energy that being a liquid provides over being a solid. When it rapidly turned into a solid, all that potential energy was released. Okay, so I'm going to show you a little video of kind of what that looks like. It's not this flash freezing demo because I couldn't find that anywhere. Okay, but I did find something else. All right, so where we're headed with this is being able to calculate how much energy would be required to do something like this. Okay, now I don't remember if we actually did this one before Christmas or not, but we're going to go over it. Okay, because I know a lot of people weren't here. Okay, so we're going to do this one. We want to figure out how much energy is required to heat 250 grams. Okay, so we know the mass of ice at minus 15 until it's steam at 150. So the first thing I do in a question like this, where I know the state of the material is going to change, is I draw that heating curve of water. Okay, which was the graph I had there on the last question. In fact, instead of drawing it, I'm just going to copy it over. Okay, so on this question, I'm going to be starting about here at minus 15 degrees, and I'm going to end up here at about 150. Okay, so I'll just extend my graph a little further. Okay, how many steps are there to this question? Like how many different calculations? Right, I'm gonna have to do 5 different calculations. The first thing we have to do is calculate how much energy is required to heat the ice from minus 15 to 0. That'll be step 1. Then I'm gonna have to figure out how much energy is required to melt the ice. It's not gonna change temperature during that part, it's just gonna melt. That'll be step 2. Okay, then I've got to heat the water to its boiling point. That'll be step 3. Weird. Okay, then I'm going to have to boil that water off. Okay, that'll be step 4. And then I'm going to heat that water to 150. That'll be step 5. Basically, any place where the line changes direction is the start of a new step. All right, for step 1, I am changing the temperature of ice. Which formula am I going to use to calculate that? Look. E equals mc delta T. Okay, we know that because the temperature is changing. So that's the formula we use because we have a temperature change. Okay, in step 2, I'm melting the ice. There's no temperature change this time. E equals mLF. All right. In step 3, I'm changing the temperature of the water, so we're back to this one, E equals mc delta T. In step 4, we're boiling the water. Now there's no temperature change. Which formula do I use here? Okay, go. E equals mLV. Right, and then on step 5, we're back to mc delta T because we have a temperature change again. Okay, so now we've decided what formula is going to be used for each step. Now I've got to decide what are my numbers. Right, so for step 1, okay, they already said that we're dealing with 250 grams. That's 1 cup. Okay, it's 250 milliliters, 1 cup, okay, of water. Well, in this case, ice, because that's what we're starting with. So we'll have 250 times the specific heat capacity of ice, which is 2.116 joules per gram, and multiplied by the change in temperature. Well, we're going from minus 15 to 0. Okay. If this was a question that involved cooling something, would I use a negative number? Yes, I would. And that would indicate that instead of using energy, it's now losing it. Okay. All right, so we'll calculate that here in a minute. Okay. Actually, we'll calculate it now. All right, so we got 250 times 2.116 times 15 degrees. So that's going to take 7,935 joules. All right, first step is done. Step 2, I take the mass. Do I still have 250? Yes, and I'm going to have 250 all the way through. That's not going to change. 250 grams times the latent heat of fusion, which we said was 333 joules per gram. All right, 83,250 joules. Is that a lot more energy than it required to heat the ice? Yeah, and that's usually the way it is. Usually a state change requires more energy than a change in kinetic thermal energy. All right, step 3. I've got E equals mc delta T. I still now have 250 grams, but now it's water, okay, times the specific heat capacity of water, which is 4.2, okay, times the temperature change. How much am I changing the temperature by? 100 degrees. Okay, so 105,000 joules. And for those of you that took French immersion, that's not a decimal. Okay? In English, decimals are periods, like they should be. Commas are used to separate groups of thousands. As I had someone who did that wrong. They took French immersion and they thought I was writing a decimal the whole time. And they did this wrong on their unit exam because that's what they thought. So I'm just clarifying. I'm making a little joke, but I'm also clarifying. That's not a decimal. Okay? All right. E equals MLV for step 4. Okay, so our mass is still 250 grams. Like we said, that's not going to change. And we're going to multiply that by LV, the latent heat of vaporization for water. Is the latent heat of vaporization different for different materials? Yes, just like specific heat capacity is different for different materials. Okay, 2,260 joules per gram. Is this going to be a big number? Yep. 565,000 joules. Okay. And then lastly, I need to heat the steam that I now have because I've evaporated all the water. Okay, so 250 grams of steam times the specific heat capacity of steam, which is 2.02, okay, and multiply that by 50 degrees Celsius. Okay, 25,250 joules. All right, what's my last step? Yes, all that's going to be on there. All the specific heats will be on there. All the latent heats will be on there. Okay, if they're not, they're in the question, or it's what you were asked to solve for, or something like that. Okay, all right. Last step. Add them all together. Okay, so plus 565,000 plus 105,000 plus 83,250 plus 7,935. All right, so our grand total is 786,435 joules. Okay, question like that would probably be out of 12 marks. I would not give you one that had that many steps on an exam because it just tells me how fast you can do it, not whether you can do it. So expect that one on an exam would probably have a maximum of 3 steps. Okay, it would either be 2 temperature changes and 1 state change, or 2 state changes and 1 temperature change, or something like that. But it would probably just have 3 steps on a unit exam. Okay, questions there? Okay, but that is exactly the kind of thing that I'm going to ask you to do as a written response problem on Thursday. Okay, do you have to manipulate anything? You just have to plug numbers in. So it's pretty easy marks. Okay, just like the specific heat capacity problems are pretty easy marks. All you got to do is manipulate E equals mc delta T for something, right? Okay, so those should be pretty straightforward. All right, so talking about a couple of things here. Okay, this, I believe, is in the worksheet package. We'll just pull that up. But what I want you guys to do is give me some explanation answers, okay, for 1 through 5, and then 6 through, I think there's up to 11, maybe there's even more than that. They're all the kind of problem solving questions like we just did. Okay, so we'll call those up here. Okay, so why does putting ice cubes in water make your drink cold, or whatever your drink is? Okay? When you put ice cubes in it, it stays cold. Why? Right, it absorbs energy from the drink. It isn't because the ice cubes are cold. Basically, once you throw them in the drink, they're going to be at 0 degrees Celsius. They're going to warm up very quickly. We saw in the example we did, it doesn't take very much energy to warm ice, but it takes a lot of energy to change its state, to melt it. Okay, and that's what they're doing. They're absorbing energy from the drink as the as the drink absorbs energy from the surroundings. The ice cubes will then absorb that energy and keep your drink cold for longer than it would stay cold if you didn't have them in it. Okay, same reason why we put ice in a cooler. Okay, it absorbs a lot of the energy and it absorbs it for longer because it has to change state. We don't fill a cooler with cold water. Okay, because that cold water is just going to warm up. Ice has to melt first and then warm up, so it has a greater ability to absorb energy. Okay, when we sweat, that cools us off. How? Right. It takes a lot of energy to evaporate water into a vapor. And as sweat evaporates from our body, it takes the energy from our body to do that. Okay, before Christmas, we were talking about that's why when you get out of the shower, you feel cold. The water on your body is starting to evaporate. Okay, you feel warmer once you get dried off because now that water is gone. It's not evaporating, stealing energy from your body. Okay, gardeners will often spray their crops before a frost. This prevents the products from freezing. If you get a thin film of water on the plants, what will the thin film of water do? It'll freeze. Does it release energy when it does that? Where does the energy go? Into the plant. It keeps the plant from freezing. Okay, the water on the outside might freeze, but the plant itself will not. Okay, now that only works if it isn't going to freeze very hard. Okay, we're talking like it's going to be -1 or -2. Okay, that's the word. That if it gets any colder than that, everything's going to freeze and die anyway if you don't cover it up. Okay, this is essentially what you would do if you had an orchard with like maybe grapes or apples or something like that. Okay, it's not going to protect the delicate leaves of a tomato plant from freezing. They're going to die if it gets to be like 2 degrees above 0. Okay, they seem to just get stroked no matter what. We talked about this one already. Which is better at keeping food in a cooler cold, 10 kilograms of ice or 10 kilograms of water? Well, 10 kilograms of ice. Even though they're the same temperature, ice still has to change state. And for every gram of ice that's in there, that's 333 joules of energy that can be absorbed. Okay. All right, how are we doing on the calculation ones? Okay, first few are pretty easy. They're all like one-step kind of calculations. Okay, but as you get further down, especially as you get to the additional ones here, okay, these are multi-step. Okay, so you'd have to draw the heating curve and go from there. All right, so I'll give you a little longer to get ahead of me again, and then we'll go over those together. Okay.